Hi, and welcome to Dr. V's Chemistry Webcast. I'm Dr. V, and today we're talking about average atomic mass calculations for elements. What I'd like to accomplish in this webcast is to discuss the relative abundance of isotopes, review weighted averages, and show you how we use weighted averages to calculate the average atomic mass for an element. Let's start by talking about boron. Now, the element boron has two naturally occurring isotopes. Isotopes are atoms of the same element with the same atomic number but different atomic masses. The two common isotopes of boron are boron 10 and boron 11. Boron 10 has 5 protons and 5 neutrons. It's got to have 5 protons to be a boron atom. We call it boron 10 because there are 10 nuclear particles, or nucleons, 5 protons, 5 neutrons. Boron 11 also has 5 protons, which is required for it to be an atom of boron, and it's got 6 neutrons. So a total of 11 nuclear particles or nucleons, and so boron 11. Boron 10 has a mass of 10.01 AMU when we measure it precisely, and boron 11 has a mass of 11.01 AMU when we do very precise measurements of the mass. Now, the other relevant part is that boron 11 is far more abundant than boron 10. If we look at a very large sample of boron in nature and we start looking at the masses of the different isotopes and how common boron 10 is versus boron 11, turns out that 80% of all the boron atoms that we find in the world have a mass of 11, and 19.9% of them have 10 for their mass. All right, we can see that on this mass spectrum of boron. This becomes really important because they're not equally abundant. And so when we go to think about the atomic mass, or the average of the atomic masses for boron, the fact that we have lots more boron 11 than boron 10 becomes really important. We need a weighted average here, not a mean. A mean would say, okay, I've got 10s and 11s, I'm add them up and divide by 2, which would give me an average of 10.5. But that doesn't take into account that I have lots more boron 11 atoms. We want to do that weighted average. We want an average that's closer to 11 and not the midpoint. We don't want the arithmetic mean. We want a weighted average. How do you do a weighted average? Well, they're really pretty simple. And once you know how to do them, they all kind of work the same way. So to find the average atomic mass, we're going to do the percent abundance over 100 times the isotope mass of that same isotope and do that calculation. And then we'll do the percent abundance over 100 times the isotope mass for the next isotope and do that math, and then keep going until we've accounted for all the isotopes present. For boron, there are only 2. So let's actually do it. Got the data for boron 10, the percent abundance, and the atomic mass for boron 11 as well. So let's set up that weighted average. I'm going to do 19.9 times 10.01 divide by 100. I'm going to do 80.1 times 11.01 divide by 100. This is how I set it up. This is what you should write down on your paper. And then I get out my calculator, and that gives me an answer of 10.8 AMU for the average, right? Because I've got more boron 11, I need my weighted average to be closer to 11 than 10. And that's what we see here. Now that we know how to do the calculations, let's do another problem. What's the average atomic mass of neon? Neon has 3 stable isotopes: neon 20, neon 21, neon 22, and they have different abundances. You'll notice, right, it's really apparent from the table, over 90% of all the neon atoms in the world have an atomic mass that's just about 20. Less than 1% have a mass that's just about 21, and only a little over 9% have an atomic mass of just about 22. All right, so we have lots of precision here in our answers, but it doesn't affect how we set up the calculation. It's still percent abundance times atomic mass for isotope 1, repeat for isotope 2, repeat for isotope 3. And then we set things up in our calculator. So to find the average atomic mass of neon, I'm going to do 90.48 times 19.992 and so on, divided by 100 for the neon 20. And then my next set of parentheses are for neon 21, 0.27 divided by 100 times 20.9938 and so on. And then for isotope 3 for the neon 22, 9.25 divided by 100 times 21.991 and so on. So I've got these 3 calculations in the parentheses. I'm going to set them up in my calculator. I'm going to type everything in. And what do we get? 20.18 AMU. As expected, we get an average that's closer to 20 than any of the other isotope masses. And that's what matches the periodic table, which is our clue that we've done this calculation correctly, because we've accounted for the relative abundance of neon 20 being way higher than for the other 2. Once you know how to do the calculations, they all pretty much work the same way. There are some twists, but that's not really the intent here. I just want to make sure everyone can do average atomic mass calculations. So just to summarize, elements can have different isotopes, and those different isotopes have different atomic masses. And the isotopes will have different abundances. And so to account for that correctly, we're going to report a weighted average of the isotope masses where we weight them based on their percent abundances, and that's the information that shows on our periodic table. The masses on the periodic table aren't integers. We're looking at these weighted averages. I hope you found this helpful. If you did, leave a comment and subscribe to my channel so you get all my latest updates. It's always a good day to study chemistry.